the limited supply of traditional fossil fuels and its cost, the environmental damage caused by carbon dioxide emissions, and a growing public awareness of environmental protection are the reasons for the worldwide initiatives in the exploitation of renewable energy sources such as hydrogen. Hydrogen is the most promising fuel for road transport due to its abundance, efficiency, low carbon footprint, and absence of other harmful emissions. Hydrogen-powered vehicles such as vans, buses, and scooters have been prototyped and are being trialed on roads by various companies and government agencies in order to explore the barriers associated with hydrogen vehicle adoption and the interest of the public. So why hasn't the interest in hydrogen-powered vehicles picked up? The problem is pressurized hydrogen stored in the tanks, which has led to a number of accidents and injuries during their storage and transportation. The fuel tanks are stressed during continuous cyclic loading between ambient and storage pressures. Stress results in the development of fatigue cracks. When hydrogen gas comes in contact with atomically clean cracks, it dissociates through a process called hydrogen embrittlement, which also reduces the structural integrity of the tank. The growth of fatigue cracks due to stress or hydrogen embrittlement may lead to catastrophic tank failures. SafeHPower, a European-funded FP7 project, is here to address the safety concerns surrounding hydrogen. The overall goal of the project is to provide continuous monitoring of the entire storage and distribution system, ensuring that all defects that would eventually cause leaks or catastrophic tank ruptures are detected in time. SafeHPower has proposed two innovative technologies to monitor the creation and growth of fatigue cracks and conduct 100% volume inspection of hydrogen fuel tanks. Based on acoustic emission technology, a single sensor system has been developed for the continuous monitoring of vehicle tanks made from a composite material. Juan Chacon has the details.
The system consists on an acoustic emission sensor which is attached to the surface of the tank, and we have designed an enclosure. This enclosure protects the system against electromagnetic interferences. It also includes an amplifier which amplifies the acoustic emission signal. The system has been designed to be powered through the battery of the hydrogen-powered vehicle. The microcontroller has been programmed in order to extract some features from the acoustic emission signal, so when it detects a defect in the tank, a light will be activated in the dashboard of the vehicle. The main advantage of the system is that it detects the defect at a very early stage before it becomes critical.
The acoustic emission sensor system for vehicle tanks will detect any defect that threatens the structural integrity of the tank. The minimum detectable defects are 5% of the tank wall thickness in the radial direction and 10% of the wall thickness in the direction parallel to the longitudinal axis of the tank. The system is also built such that it can use power from the car battery. Finally, it generates a dashboard warning light to alert the driver when the tank needs to be taken to a service station for a total volumetric inspection using a higher resolution technique such as neutron radiography. For large storage tanks made of steel, a higher level acoustic emission system consisting of 3 or more sensors and an extensive signal processing software has been designed.
The acoustic emission array system for a large storage tank is a system that uses a novel signal processing algorithm based on wavelet transforms to detect a defect. A computational method has been specifically developed for this system to process and handle data from multiple sensors over long loading cycles. It uses the triangulation method for the location of defect in a tank. The graphical user interface shows the location of the defect while hiding all the complex computation processes that take place in the background.
Under the SafeHPower project, the neutron radiography technique was investigated to conduct total imaging of defects on hydrogen storage tanks. The sensitivity of neutrons to hydrocarbons makes neutron radiography very attractive for exploration to image defects on a variety of materials, including metals and composites. In principle, a neutron source, a collimator, a jig to hold the specimen, and an imaging device are needed to perform neutron imaging. However, an optimum energy, a high neutron flux, a bespoke collimator, and a suitable scintillator are essential to obtain contrast and high resolution on the image. SafeHPower proposed a tangential neutron radiography system using a portable deuterium-tritium neutron generator. A separate slide video presentation has been uploaded to the SafeHPower website with details about the technology, various experiments, and the results.